We're given a histogram which shows information about the lengths of a sample of worms of a certain species. Here we go, frequency, density, and length. Remember, we have to use a histogram when the intervals are unequal. We actually don't quite know how it was investigated here, whether it was between 0 and 1, 1 and 2, or whether this was like a single interval. But in any case, we've got a histogram and we're plotting frequency density. We don't have a scale on the graph, but we do know the lengths. And we're told the number of worms in the sample with lengths in the class 3 to 4 is 30. So I'm going to talk about two different ways of doing part A, find the number of worms in the sample with lengths in the class 0 to 2. Method 1 is to try to get the frequency density labeled along here. So I've got the frequency, and therefore the frequency density is equal to 30 divided by the class width, which in this case is just 1. So actually the frequency density is 30 from 3 to 4. So I know I can label that as 30. And actually it's then quite quick to label the rest of the graph. I'm just going to go up in tens, but you can see this would be 8. And that is enough to find the number of worms. Well, it's just going to be, to get the frequency, it's going to be the frequency density times the width. So it's going to be 8 times 2, 16 worms. So that was method 1. It works quite well here. And actually, I think it's my preferred method. Method 2 is along very similar lines, but actually, we use straight from the start. I mean, I have used it, but I didn't really talk about it. The fact that essentially it's the area that's the frequency. So I can look at the area of 0 to, sorry, 3 to between 3 and 4. And that area is worth 30 worms. And I can count the squares. Now, actually, there are 1, 2, 3, 4, 5, 6 big squares. And sometimes this method that I'm using right now comes in really useful because if you can just kind of count the big squares other places, like, this would be 2 big squares, and you can easily go from here to here. For example, if this is 30, well, this is just 3 times as small. So this part is just going to be 10. It's a little bit trickier when you've got lots of these small squares as well, though, not an entire big square. So I'm going to do it in a slightly different way. I'm actually going to count these little small squares. And because I've got 6 big squares, and in each big square I've actually got 25 squares, 5 times 5, then it's 6 times 25, and it's going to be 150 small squares. You can also get that by counting how many go up, which is 30, and timesing that by 5, 150. So that means that, well, must be that one worm is going to be 5 small squares. We could also work out what one square was worth if we wanted. I might need to do that, but now I'm looking at here. Okay, and I've got 8 squares going up and 10 across. So therefore, 80 squares. Okay, if I know that 5 squares is worth 1 worm, I just need to divide through by 5. 80 divided by 5 worms, which gives me 16 worms. So it's just a slightly different way of doing the problem. First method, I actually calculated the frequency density and then worked out the area exactly. The second one, I'm using these little small squares, but essentially they are the same method. They just, they feel a little bit different. For part B, we're asked to find an estimate of the number of worms in the sample with lengths in the range 4.5 to 5.5. Now, the reason this is an estimate is that we don't really know how it's spread. All we know is there are some worms between, 1 and 2, but they might all be at the upper end or they might be at the lower end, but we're kind of assuming that they're spread evenly. And it's okay when you look between 0 and 2 because you end up getting them all. But when you look between 4.5 and 5.5, we're not entirely sure. It doesn't really matter. I just wanted to explain why it was an estimate. So essentially, I want to find this green area here. Okay, method 1 is to use my frequency density again. So I'm gonna, I can see that this is going to be 24, and I'm going to times that by 0.5. So that gives me area 1, this bit on the left. and then I'm going to add, it's going to be 12 times 0.5. So that gives 12 plus 6, 18 worms as my estimate. Now, method 2 does also work. It's a little bit trickier. So now, remember, we're trying to count how many little squares there are. And it's a bit awkward because, yeah, I've actually got 2.5 along here. So it's going to be 2.5 times, and then I need to count how many are going up. We've got 5, 10, 15, 20. Okay, it's 20, it's 24 again. And then I've got 2.5 over here, and I'm going to be timesing that by 12. So I need to figure this out. That is going to be 60 plus 30, 90 squares. Remember, 5 squares represented 1 worm. So to get the number of worms, I now need to divide by 5, which again gives 18. So I've talked about 2 different methods. I personally think the first method is the best one in this case, but I wanted to talk about the second method because in other situations, you can do things really quickly. I'm talking about if we were like, imagine 8 to 9 was just this, then you can literally say, right, well, this is 30. So that means that 1 square is clearly 6, and therefore this is 6 and this is 6, and we get 12. Okay, so it's that quick rather than having to work out the scale. Sometimes the scale can be harder to find as well. So that's why I wanted to, talk about it. Anyway, we've done it 2 different ways. These are our answers.